Now, for the sake of, for example, IPsec VPNs or SSL VPNs or any kind of secure VPNs, where if we have, for example, let's look back at our diagram in here, and let's suppose, like, again, this is going to be, we have those two sites of ours. This is going to be site A on the left side, and this is going to be site B on the right side. And we have that routed feed to be like the transit network. The hash function by itself doesn't provide enough security for data in transit. It provides enough security for data at rest. Like, for example, when you store in the database a password of a user, instead of storing it in clear text, it's good enough to store it using a hash value. That's going to be good enough. But even though nowadays not even storing data at rest and protecting it for integrity reasons, we no longer use just a regular hashing function because it still has its own vulnerabilities in there. So nowadays, it doesn't matter if you want to provide integrity for data in transit or data at rest, we're going to use an advanced version of hashing. Because let's see what is the problem with hashing, and I'm going to speak about the example of data in transit. So what this means is that if we want to send, of course, let's suppose we have an a VPN tunnel, IPsec or SSL tunnel between, let's say, ASH3 and router 1. So we have an IPsec tunnel between ASH3 and router 1. There's an IPsec tunnel in there. And we're going to send data between our sites through that IPsec tunnel, which means we're going to provide some kind of security by sending data in that IPsec tunnel or SSL tunnel in there. So let's see what is the problem with hashing. So if we would want to inject a packet in that tunnel, this is the packet with the layer 2 header, with the layer 3 header, with the payload layer 7 header, doesn't matter. Of course, it depends on the type of the tunnel. If it's SSL or IPsec, we're going to protect different portions of the packet. But to keep it simple, this is my packet, which I want to send in that tunnel, IPsec or SSL tunnel. This is my packet. And what I'm going to do, I'm going to take that packet, put it in my MD5 hashing, in my hashing function, whatever that is, MD5 or SHA. And a hashing algorithm, let's say it's going to be MD5, just for the sake of it, MD5. And we end up with a fixed hash, which is very small, which is 128-bit in size. So what happens? I'm gonna attach that hash value to my data before I send the traffic in the VPN tunnel, SSL or IPsec. So I'm gonna pen in here that very small size of 128-bit, which is the hash value. This is my hash value, which is 128 because 128-bit in my case, because I'm using MD5, so hash value. Now, as this packet is being sent in the IPsec tunnel, somebody in transit like router 3, because it's gonna, let's say it's gonna see that packet in there. So what it can do, it can take the packet, modify it, like change the content. It can take the packet, modify it, so change the packet. So this was the initial packet. The attacker in the middle receives that packet. It behaves like a man-in-the-middle attack. That router receives the packet. It changes the packet value to whatever that attacker wants. So this becomes the altered or the modified packet by the attacker. So the modified packet is going to also put that packet in the MD5 hash engine, end up with a hash value of 128-bit, and of course is going to now append the new hash value of the modified packet to the packet. So it's going to append the new or the modified hash value to the packet. So now what this means is that, and of course it's going to then route a packet further to the destination. The new is going to route the packet. So this is what the initial packet was received by the attacker. It changed the data. It recomputed the MD5 hash, and then it injected the data back in there. And when the destination receives the packet to validate the data, so how do we make sure that packet was not modified in transit? What the receiver does is going to receive that packet, put it in the MD5 hash engine, end up with a hash value, and compare that hash value with a hash value attached to the packet. And if they match, it means the packet was not modified, right? But unfortunately, the problem with hashing function, as we saw in here, is that because hashing only takes as the input value the data itself, nothing else, it means that anybody in the transit path could capture the data, change it to whatever value they want, recompute the hash, attach the new hash value to the packet, route it back in the network, and nobody can detect that the packet was modified in transit because the attached hash value to the packet matches the packet, the resulting hash of the packet. So because of this reason, we actually are going to make use, if we want to provide integrity, we're going to nowadays make use of what I call the keyed hash message authentication code. So we end up with this functionality because, as we saw before, regular hash functions cannot defend against man-in-the-middle attacks. And what this is just as the name implies, it's a keyed HMAC. It's a keyed message authentication code algorithm, which it's a variation of hashing named HMAC, which what this means is that HMAC uses as input, as seed value to the algorithm, not only the data, but also a secret string or a secret security key, which is only known by the sender and the receiver of the data. So what this means is that if we take the same example as before, with the same two sides of ours, left and right, and we have that tunnel between router 1 and ASH3. And as traffic flows, let's say in this direction through the tunnel, from router 4 to router 1, distant to server A. So router 1 and ASH3 are only the endpoints of the VPN tunnel, but in the end traffic flows between router 4 and server A. So if what router 4 sends in the tunnel is going to be, let's say, the payload. So let's again put in here the payload. So the initial packet. Now HMAC means that what I'm going to put in the MD5 hash engine, so in the hashing engine, I'm going to put as the input both the packet, the data, and a secret key, which is known only by the VPN endpoints, by ASH3 and router 1. It's not known by anyone else anywhere. So we put the seed changes now to not only the input data, the packet value, but also that secret key. And of course the result is going to be a hash value of 128-bit if we use MD5. So then what happens now, ASH3 is going to now append to the packet this MD5 hash, but of course now it was computed differently, using as input not only the data but also that secret key. So I'm going to put in here the hash value, 128-bit hash, Now when var1 receives the packet, it's going to receive exactly this packet in there. What var1 does is it takes that packet. So this is exactly the packet that, let's say, var1 receives through that IPsec or SSL tunnel. So var1 does the same thing. It's going to take the data, the packet size, the data itself, plus the same secret key, which also var1 knows as well as the same key as ASA3 has. It's going to take those two inputs, put them, it's going to take the packet and that secret key. That's what var1 is going to do. var1 is going to do is going to put that the input as the secret key as in the packet in the MD5 in the hashing engine, and it clearly is going to end up with the same hash value as appended to the packet is received. So it's going to end up clearly with the same 128-bit value as it was actually attached to the packet itself. So from var1's point of view, this means that packet was not modified in transit. And if somebody modifies the packet in transit, so if that attacker in the middle is going to capture the packet and let's say change the data. So let's say the attacker in the middle in here is going to capture the packet, change the data, the payload to whatever other value packet. Let's say the payload to be the new packet information, the new data information. When they want to compute the MD5 hash or the SHA hash or whatever algorithm is going to be used and attach the hash value to the packet, there's no way they can end up with a correct hash value in here, because the attacker in the middle doesn't know that secret key to be added as the input to the hash algorithm. So because the input is going to be different on the attacker side, the attacker can put as input as seed to the hashing algorithm only the packet but not the secret key, because the secret key is not known. Only the VPN gateway is not the secret key. It clearly means that if the attacker in the middle is going to change the packet and compute a new hash, when var1 receives this modified packet, when var1 receives this packet in here, he's going to put in the MD5 hash engine the packet received, the data, and that secret key. He's going to put that information in the hashing engine. And because the input is different on var1 than it was on the attacker, because var1 also uses that secret key as the input, clearly the resulting hash value performed by var1, the resulting hash value, so this value in here, I'm going to use the color of, let's say, orange. This value in here is not going to match what is attached to the packet, because the attacker and my VPN gateway, the receiver, use different inputs in the hashing algorithm. The attacker cannot use the secret key because he doesn't know it, but the VPN gateway knows the secret key, so he's going to always put that input in the hashing algorithm as well. So that's how nowadays we actually protect data both in transit and at rest against unauthorized changes, because as an input of the hashing function, we not only put the data itself but also a secret key which is now known to an attacker. And if we look at in here at so what I showed you so far at Cisco is a Cisco Press book, the one of the books, Cisco Press, Cisco Secure Virtual Private Networks. It's a very old book from 2002, but it's very good. So if you use at HMAC, look at HMAC in there at a figure. There we go. So they show in here pretty much the same thing, which means that HMAC, what it does is that it has as the input the clear text message, which is variable in length, and that secret key. Both of them serve as the input to the hashing function, not only that clear text message, the data itself. And of course the output is going to be a fixed length hash value or checksum or fingerprint or whatever in there, which is going to be, depending on the use algorithm, is going to be 128-bit or 256 or whatever value it is in there. Okay. Now let's speak about encryption. So encryption, as opposed to hashing, where hashing was a unidirectional or one-way mathematical function, because the scope of hashing was not to, scramble the data as being sent on one side and on the other side to be able to make the real data back. The scope of hashing is just to prevent unmodified, unauthorized changes to the traffic. Now encryption is different. Encryption has a scope to just hide the data in transit or at rest, so that unauthorized parties like attackers or whoever else is not authorized should not be able to read the clear text data. So for that reason, encryption, it's a two-way mathematical function which is used to provide data confidentiality. It's a two-way function because one side is going to encrypt the traffic, which means it's going to take the plain text readable data and using the encryption key as the input, and of course the used algorithm is going to end up with the output is going to be a ciphertext which is unreadable. So what this means is that when we perform encryption, and we take again that example with the VPN tunnel and those two sites of ours, and we have that VPN tunnel between ASH3 and router 1. That's secure VPN tunnel. Because as you're going to see, VPN doesn't necessarily mean security. And what this means encryption-wise is that if we want to send a packet in the VPN tunnel, so this is my packet, which is size, let's say, 1000 bytes. I'm going to take that clear text data plus the encryption key, which again is something which only the VPN gateways know those keys back and forward. And the input, the clear text packet plus the encryption key, I'm going to put those values in the encryption algorithm, which we have a couple of options, encryption algorithm. And the result is going to be what they call the cipher data. There's going to be a new packet without the, of course, without the specific VPN encapsulation. It's going to be the same size in there pretty much. But this packet, if you capture that packet, which is going to be the encrypted packet, if you capture that packet, you cannot read, you cannot understand what's in there. So data is being scrambled by an encryption algorithm, so that if somebody captures that packet in transit, they're not going to actually see what was actually sent in the packet to begin with. So that's the encryption part. And when the packet and this encrypted packet is going to be actually sent, this encrypted packet is going to be sent through the VPN tunnel to router 1. When router 1 receives that packet, receives this encrypted packet, it's going to take that packet plus the decryption key. Is going to take those values, so the received ciphertext, the encrypted packet, and the decryption key is going to put those in the encryption algorithm. And the output, so that's the input, the encrypted data and the secret and the decryption key, is going to put those two in the encryption algorithm, and then the output is going to be back the clear text packet which was sent by the sender initially to begin with. So that's why it's called a two-way mathematical function, because the process is reversible. So one side is going to encrypt the traffic, which means it's going to take the plain text data plus the encryption key. That's going to be the input to the encryption algorithm, and the output is going to be the ciphertext, which means the encrypted data which is unreadable. And the other side, when it receives the packet, is going to take as input the ciphertext, so the encrypted traffic, and the decryption key, and that's going to serve as the input to the mathematical algorithm. And then the output is going to be back the original data, which is plain text, which is readable, which was actually what the initial sender actually wanted me to read, the clear text data. So it's a two process. One side encrypts traffic, the other side decrypts the traffic. That's why it's a two-way mathematical function, because the process is reversible. Now, of course, likewise, just like in the hashing algorithms, the strength of the encryption is based on both the algorithm. The newer the algorithm, it means it's more secure because it has fixed any kind of design flaws in all the algorithms. And of course, likewise, the larger the key length, then the more secure the algorithm is in the end. Because the larger the key length, it means that you have the larger the key length, it means that technically speaking, it's more many keys which are available, possible to encrypt and decrypt that data. So the larger the key space, basically, for encryption algorithms, it means that the larger the key space is, the larger the key size is, it means you have more possible keys which were actually used to protect that traffic back and forth, which means is much more difficult to actually, break that encryption and identify the keys which were used to encrypt traffic in order to decrypt it and see the clear text data. An attacker, of course, would do that. Now, we have two types of algorithms from the encryption point of view. We have what is called a symmetric algorithm, which means that on that VPN tunnel, the same key is going to be used for encryption and decryption. This is also known as shared key encryption algorithms. These are computationally efficient, which means it's very cheap to perform this kind of encryption and decryption in hardware. Because you can imagine nowadays, if we want to, encrypt line with 100 gig, we have to do that in hardware. Also, even like, on regular Cisco routers, which have 100 megs of encryption performance, or 200 megs or whatever, most of them have, if not built in, they have the option to add a hardware encryption module to do the encryption and decryption process in hardware, not in software. So because the same key is used for both encryption and decryption, and because the key size, it's not that big, it's between 56 in general and 512 bits, it's very cheap and very easy and scalable to do encryption and decryption in hardware if the algorithm being used is symmetric. We also have asymmetric algorithm, and as the name implies, being asymmetric, it means that a different key is used for encryption as opposed to decryption. So what that means is that if one side uses one key to encrypt traffic, and when the other side receives the packet, it's going to use another key to decrypt the traffic. This is also known as public key encryption. And because it's a very complex mathematical function behind the scenes, and it's very computational resource, it consumes a lot of resources back and forth, it's very expensive to perform this in hardware, and pretty much it's not really performed in hardware. Of course, it depends. It's not a long discussion, but in general, it's not performed in hardware. And as we're going to see, also it's performed in hardware, but it's very expensive. And as you're going to see in the end, you're going to have a better understanding of where would use symmetric algorithms, where would use asymmetric algorithms. And it's going to make much more sense at that point why the asymmetric algorithms are pretty much very expensive, and why, in which cases, would you use symmetric or asymmetric encryption in a real-life production environment. Now, the key length varies between 512 and 32768 bits. But this doesn't mean it is more secure. So even though, yes, I stated that the larger the key space, the larger the key size used to encrypt and decrypt traffic, the stronger the security. Of course, this comparison has to be done between algorithms of the same type, between algorithms of type symmetric or of type asymmetric. You cannot compare those two in between because they use different mathematical functions behind the scenes. So now, if we look at in here at Wikipedia again at cryptography, so just a visualization of both of those types of protocols. This is symmetric encryption. So symmetric encryption means So we have two sides, let's say the VPN tunnel, which one side is going to be Bob and the other side is going to be Alice. So those are our, let's say, VPN tunnel endpoints. And as Bob sends traffic to Alice in that VPN tunnel, now hello Alice is the clear text data, the input. I'm going to take the clear text data plus the encryption key, put that in the encryption algorithm, which means I'm going to encrypt the data, and the output is going to be the ciphertext, which means it's not readable in transit. So this is what devices in transit are going to see, that data, which really it doesn't mean that in there it's hello Alice. But of course Bob has used to encrypt the traffic this secret key. So you can see in the encryption algorithm, what Bob puts in there is the clear text data, hello Alice, and the secret key, that's the input, and the output is going to be the ciphertext data. Now when Alice receives the ciphertext data, it's going to put as the input in the decryption process or decryption algorithm. It's going to put in there as input the ciphertext data and the same secret key, and the output is going to be back again the clear text data, which says hello Alice. So as you can see, both the sender and the receiver use as the seed value in the encryption algorithm the same shared key. So that's why it's called symmetric or shared key encryption, because both sides use the same key to encrypt and decrypt traffic back and forth. While if you look at the asymmetric encryption, which is also known as public key cryptography, which makes use of private public key pairs, we're going to speak in more details in the PKI section. Now let's look at the direction of the traffic where Bob sends traffic to Alice. Now to provide it with a basic understanding of how this is going to work, we're going to speak in more detail in the PKI section. Both sides of the tunnel, both Bob and Alice, are going to have, both of them are going to have a public key and a private key. Both of them have that. We're going to speak in more detail in the PKI section. But to keep it simple now, when Bob wants to send this clear text data, hello Alice, to Alice, this is the clear text data, is going to serve as the input to the encryption algorithm. Now to encrypt that traffic is going to put as the input not only the clear text data, but it's going to use as the input Alice's public key. So not its own public key, but Alice's public key. So that's going to be also taken as input to the encryption algorithm. So Bob puts in the encryption algorithm the clear text data as the input and Alice's public key, and of course the output, it is going to be the ciphertext data. Now as Alice receives the ciphertext data to decrypt the traffic, Alice is going to put as input in the decryption algorithm, is going to put as input the ciphertext data as input and its private key, its own private key, likewise as the input. So using the received encrypted traffic and its own private key as input to the encryption or decryption algorithm is going to result as the output with again the clear text data. So we're going to see, we're speaking more detail on the PKI infrastructure when we go to digital signatures and the scaling of private public key system or the asymmetric algorithms. Is that in most cases, if you and me want to send something securely using a asymmetric algorithm, I'm going to encrypt traffic using your public key, and when you receive the traffic, when you receive the encrypted traffic, you're going to decrypt the traffic using your private key. And when you send traffic to me, you're going to encrypt traffic using my public key. And when I receive the encrypted traffic, I'm going to decrypt it using my private key. But it's not always the case, because a private public key pair can be used with different scopes. but this is just for the sake of understanding the private public key encryption, or the public key encryption, or the asymmetric algorithms from the encryption point of view. So when you speak about asymmetric encryption, it means that one side uses one key to encrypt, the other side uses another key to decrypt, to keep it more simple. Because it's not always that the public key is used to encrypt and the private key is used to decrypt. It depends what you want to achieve.